Hi, I'm Howen from Georgia Tech. In this presentation, I'm going to show how graph wavefront algorithm works. Before we dive into the method, we have to know what a graph is like. Here is the definition of sequence graph. It is a directed graph, and each vertex is labeled with a string. And with this definition, we can see that each walk in the graph spells a sequence. Like the highlighted walk, it spells a sequence AAGA-TCC. We now formulate the sequence-to-graph alignment problem. That is, given a query and a sequence graph, we want to find the walk in the graph so that the edit distance between the query and the walk is minimized. For example, here we have a query and it matches the highlighted walk with minimum edit distance 1 by just substituting the G with A. The graph wavefront algorithm we developed for sequence-to-graph alignment is motivated by an algorithmic technique used in pairwise sequence alignment. Recall the DP recurrence to compute the edit distance between two strings. It fills a 2D DP matrix, and each cell in this matrix has 3 dependencies as shown in the figure. Based on the dependencies, the DP matrix can be filled row by row or column by column. And you can get the minimum edit distance in the bottom right cell in this matrix, which is 2 for these two sequences. And the time to fill this DP matrix is quadratic in the length of the sequences, that is n squared. So can we do better than this? And the answer is yes. There is an algorithm which only computes the DP cells with values less than or equal to the minimum edit distance. In this case, the mean distance is 2. So instead filling the whole matrix, only cells with less than or equal to the mean edit distance are computed. The runtime reduces from n squared to dn. D is the minimum edit distance. And one can see that when the mean edit distance is very small, the algorithm would be very fast. However, the algorithm becomes a little bit more complicated. Now you cannot fill the whole DP matrix row by row or column by column, as you don't know the mean edit distance before you compute it, and you don't know how to avoid computing the DP cells with values larger than the mean edit distance. Instead, the DP matrix can be filled along the diagonals with this new DP recurrence below. The main observation allows us to do this is that the DP cells with 1 are always adjacent to DP cells with 0 or 1, and DP cells with 2 are always adjacent to DP cells with 1 or 2, and so on. So DP cells with D are always adjacent to DP cells with D minus 1 or D. So therefore, we can compute the DP cells with 0, 1, 2, and so on progressively until we reach the bottom right cell. So let's look at this example. We start from D equals 0 and find all the cells with 0 first. Then we increase D to 1 and then find all the cells with 1. And we keep doing this until the bottom right cell is reached. We number the main diagonal as the diagonal 0, and we keep track of the offset of the farthest DP cell on each diagonal with value D outside the DP matrix as highlighted. Initially, we have a 0 as the offset since the farthest DP cell with 0 so far is their zeroth cell on diagonal 0. First, we try to find all the cells with 0. This is done by extension along the diagonal with matched characters in these two sequences. Note that any edit operation won't result in a cell with 0. So here we only have one T2T match, and after that, the characters in the two sequences don't match. Meanwhile, we update the offset of the farthest cell with 0 on diagonal 0. So we use column index of the cell as the offset. So we update this offset to 1. Now we have found all the cells with 0. The highlighted cell is the farthest cell on the diagonal with value 0. And we want to find the cells with 1. And they are adjacent to the cells with 0 and 1. So we first find the cells with 1 adjacent to 0. This is done by expansion. So we look at the farthest cell on diagonal 0, and the cells with 1 are on the same diagonal and the two adjacent diagonals, which are corresponding to substitution, insertion, and deletion operations. So we call this step an expansion because now two more diagonals are added, and we need two more variables to keep the offset of the farthest cells with 1 on these two diagonals. Now we get the highlighted cells, which are the farthest cells with 1 on each diagonal. And there can be more cells with 1 adjacent to the 3 highlighted cells. So again, we extend along each diagonal with the matched characters in these two sequences, and update the offset of the farthest DP cells with 1 on each diagonal if possible. And now we found all the farthest DP cells with 1 on each diagonal. However, we haven't reached the bottom right cell yet, so we have to repeat the same procedure and find the cells with 2. This is first done by an expansion, which found the cells with 2 near the cells with 1. We highlight the farthest cells with 2 on each diagonal. And then we extend along the diagonals to find more cells with 2 using the matched characters. And we update the offsets of the farthest cell with 2 on each diagonal accordingly. Now the bottom right cell is reached, which means the two sequences are aligned and the added distance is 2. One important thing to notice is that the DP matrix here is only filled virtually to illustrate how this algorithm works. The only information to keep and update is the offset of the farthest DP cell on each diagonal in the dashed rectangle. So the size of it is 2D plus 1 because the cell with D cannot be far away from the main diagonal, and each offset can be updated at most n times before it reaches the end of the diagonal. So the time is nd. Now we show how to adapt the diagonal alignment method we just showed for sequence to graph alignment. Here we have a graph which has 3 vertices and 4 edges. Each vertex is labeled with a string. We want to find a walk starting from the first vertex and ending at the last vertex, and the added distance is minimized compared with any other walks. Now, the DP recurrence to compute sequence to graph alignment will fill a three-dimensional matrix. We visualize the 3D matrix in 2D along the vertex dimension. Here, we have 3 vertices in the graph, so the 3D matrix can be regarded as 3 2D matrices. Within each 2D matrix, the dependencies are just the same as sequence-to-sequence alignment. That is to align the query and the vertex label. They are corresponding to the first 3 terms in the DP recurrence. The difference is that there are dependencies among the 2D matrices. That is, when the alignment walk in the graph spans multiple vertices, and the last term in the recurrence allows to transit from one vertex to another, which we show in the figure. One way to solve this recurrence is to compute the whole matrix row by row using Navarro's algorithm, a sequence-to-graph alignment algorithm. But it would be much faster to only process the DP cells with distance less than or equal to the mean at the distance, which is 2 in this case. So we propose a new recurrence below, which again virtually fills part of the 2D matrices along their diagonals. I will show you how this algorithm works with this example. So here is the initial state. Inside each 2D matrix, the algorithm runs in the exactly same way as the diagonal alignment algorithm I mentioned. So you extend along each diagonal with the matched characters, and you keep track of the offset of the farthest DP cell with 0 on the diagonal. So after the extension, we get all the cells with 0. The farthest cell with 0 on the diagonal is highlighted. The cells with 1 are adjacent to the cells with 0 and 1. So we first perform an expansion and find the cells with 1 near the cells with 0. The expansion never goes out of a 2D matrix. Then we perform extension to find all the cells with 1. So this involves the dependencies across these 2D matrices. Here, there are edges between the first vertex and the second vertex, and also the first vertex and the third vertex. So these newly computed cells with 1 are still considered adjacent to highlighted cells with 1. The extension step continues, and we extend along the diagonals to get more cells with 1. Once the cell in the last column of a 2D matrix is reached, the neighbors of the corresponding vertices are explored, and the extension step is performed recursively after you transit to another 2D matrix. So we extend along the diagonal from the cell with 1, and it reaches the last column again. So we explore its neighbor and transit to the third 2D matrix. And we extend along this diagonal, but there is no more matched characters. So the extension step stops here, and we get all the cells with 1. Since the bottom right cell is not reached yet, the algorithm continues to run and perform an expansion within each 2D matrix to get the cells with 2. Then we need to find out all the cells with 2. This is done again by an extension step along each diagonal. We update the offset of the farthest cell with value 2, And now a cell in the last column of the first 2D matrix is reached. So we check its neighbors, but none of the offsets on those diagonals can be increased. So the extension step stops here. Now the bottom right cell is reached, which means the minimum at distance is 2. So the algorithm terminates. Similarly, the matrix is only filled virtually, and in each iteration, we only have to keep the offset of the farthest cells with value d on each diagonal, which are in gray color. So we use an array to keep the offset values and a queue to keep the diagonals that contains the cells with d. So therefore, each time, only the cells with d are processed, not all the cells with values less than d. As shown in algorithm 1, we start from d equals 0 on line 5. Then from line 6 to line 11, we progressively increase the value of d and perform extension and expansion until the ending cell is reached. So in the worst case, this algorithm will just fill the whole DP matrix virtually, so the time complexity matches the time of the previous sequence-to-graph alignment algorithm. But in practice, this graph wavefront algorithm usually only computes a small portion of the DP cells when the cost is very low. So the algorithm is very fast in practice. We then present a heuristic method to accelerate the alignment. The idea is to prune the wavefront that is significantly left behind or far away from the bottom right cell. It can be assessed by the aligned query length plus aligned graph walk length. For example, here, the max sum of aligned query length and graph walk length of the DP cell in the dashed cycle is 12, since the cell means the first 6 characters of the query are aligned to a graph walk with length 6. And this metric for the cell in the triangular is just 4, since the cell indicates that the first 3 characters in the query is aligned to the first character in the first vertex. So we can prune this cell, and in the future iteration, there will be a smaller number of diagonals to explore, which reduces the runtime. So this is the graph wavefront algorithm we proposed.